Okay, our next speaker is Maarten Haest. Maarten's with MineSense Technologies, and the title of the talk is Bridging the Mine-to-Mill Gap with Advanced Sensor Data and Analytics to Optimise Operations from Pit to Port. And where have you come from, Maarten? Maarten's come from Vancouver for this event today. I remember last year we had all our speakers from abroad. Thanks very much for coming, Maarten. We really appreciate it.
Thank you for the invitation, and thank you all for being here. I think, long title, but I think I got set up well with the presentation before this. So that presentation really focused on doing really detailed exploration analysis to understand most of your deposit. And I think the message I want to walk you away with from this presentation is that that analysis shouldn't stop once we start building a mine. So I'll be showing examples of where the analysis does stop and the effects of that. So I think that's what this whole presentation is about. So let's get going. First, a bit of just taking a step back. So previous talk was all about exploration. We're doing in exploration a ton of analysis in terms of collecting detailed information, characterizing your body with surface geophysics. Once we drill holes, we do lots of analysis, metallurgical test work. And then there is a ton of time spent to actually try to build the best possible geological model, the best possible mine plan, to come up with that decision, should I build the mine, yes or no? Making a mistake there costs a company billions, and so fair enough that we spend a ton of time on that. Once we get to mining, there is a massive change. So there is still data collected, but the data is a lot less rich, and the time spent to understand the data, to come up with the best possible decision, is just a fraction of what it was in exploration. And so what we'll be seeing over the next few slides is that that then does lead to mistakes. Trucks of ore being sent to waste, trucks of waste being sent to the ore stream. And each of these mistakes, they're small. I mean, that's thousands to tens of thousands of dollars per truck. But if you add up all those trucks, we're talking about a huge opportunity here. So first, current state. So current state, most mining companies we work with, is very much univariate. So they start with their exploration, very detailed work, come up with the decision to go to mining. But then it seems like many of them essentially start over again. So they start drilling blast holes, sample those blast holes. Instead of doing multivariate geochemistry, most of them, not all of them, but most of them, take it, for example, in copper deposits down to just copper, iron, soluble copper. And all decisions are based on that. Then there is, that's what the map is trying to show there. There is often an ore control geologist going in and saying, okay, these blast holes all look the same. Let's send all of this to waste. These blast holes look the same. Let's send it to ore. But the geologist is already aware that there are a few blast holes of ore in the waste polygons, a few blast holes of waste in the ore polygons. So they're planning for dilution and ore loss. And I'll show you some numbers that is actually quite significant. And that is just money that most of you spend time on getting a good understanding, getting the best possible understanding in exploration, and we're just throwing it away in mining. So there is that breakdown in data flow. Because in mining, they then go back to that polygon average. The understanding of the mineral characteristics of each truck is therefore also not great. And therefore, when then they track those trucks to the stockpile, the understanding in these pre-crusher stocks is therefore limited as well. So there is a whole loss of material characteristics from mining to processing. That is then leading the metallurgist in the plant to say, okay, I'm not going to trust that too much, and I'm just going to do my own measurements in the plant with my on-stream analyzer, with my mining assays. And then lastly, when that metallurgist is seeing issues in the plant, the amount of feedback that goes back to mining and exploration resource models is limited as well. So I think there is a whole suite of opportunity for all of us to engage and try to get more out of this. These bottom lines are just trying to represent on a few different levels. So data richness first. Data richness in exploration is tremendous. Over the last few decades, we have really expanded that data set. Data density is a bit less because you're white space drilling, but that is the nature of it. However, the time to work with that rich data is long. So there is a lot of time to actually get the most out of it to get to the right decision. Then there is that breakdown towards mining. In mining, much less rich data, but significant density because the blast holes are drilled close together. However, that mine geologist, the mine planning engineer, they really just don't have much time. So anything we do in terms of increasing data richness needs to be able to also deliver a semi-automated integration because they will not have time to look at all the extra data, for example, we collect in exploration. And the same story towards processing, so a bit more data richness. They got a few more sensors, they do, a few more measurements, but again, very little time to actually use those results. So whatever we come up with, it needs to be semi-real time and it needs to be integrated into the mining and processing decision system. And so what is the opportunity? One opportunity is, what if we could measure at the mine face? Then we could actually get the characteristics of each truck as it is getting loaded. We'll hear a lot more about that. This is just an example of each dot here is actually a truck with the material characteristics measured at the mine face. And you readily see ore trucks that are blasted on top of waste trucks that are blasted on top of ore. If you wouldn't measure it there, then those trucks would actually be lost to the waste dump and lost forever. And then these waste trucks would go to the crusher. So I think that's one really important measurement point. By measuring at the mine face, you can now have that grade of your truck, and that, by having that accurate, suddenly you can start building high-resolution stockpile models. When those stockpiles are reclaimed to the plant, again, you can measure with a front-end loader, and you can get really accurate in what material characteristics are going into the plant. And then lastly, if you can then also measure on the belt in the plant, then you can get really informative to the metallurgists about what's coming at them. They can plan for it. You can build models of stockpiles in the plant, so that's of course our stockpile there. And you can really tell them the next 2 hours, this is on average what is going to come to your milling and flotation circuits. So I think that is the opportunity to equip it with more sensors so that you can then also learn things on one end of the mining value chain and take that information back. So can you now find correlations between the sensors in the plant, the recovery, and then start building or updating your recovery models on the exploration site. So what does this in total? So we get far richer data across the value chain. We break down a lot of the silos. The data does get denser, and by being denser and more continuous across the value chain, you do have more time available to react. And so that's essentially the introduction of what MineSense is trying to do. We're trying to get sensors across the value chain and then having them work together. Before we get to examples, just a few highlights of MineSense itself. So MineSense is a Vancouver-based company. That's where our headquarters is. It grew out of a UBC research project in 2008. Right now, MineSense has become a sizable company, over 260 people. It did take MineSense 10 years to go from initial IDs to first commercial deployment, so that was a long time coming. In the 8 years since, we are now installed at 16 mines with 35 systems. So we have grown a lot. And I think because of that, the company has received quite a few awards. Focus of MineSense as a company is on copper. Why copper? Because copper has very strong heterogeneity at the mine face. So if you're building a mine face sensor, you might as well focus on that commodity. Secondly, the sensor we use is XRF, and that XRF system is very sensitive to copper. And lastly, because of the copper market being what it is, very strong market demand. So that's the sites we are working with, mostly in the Americas, and then the system installations we have. So we, all the sensor installations are on front-facing digging equipment, not on backhoes. That's a development coming. But it's any front-facing digging equipment, from electric cable shovels, hydraulic excavators, or front-end loaders. We modify our application package to fit all of them. Same sensors are being installed on belts, and then we also recently did some underground LHD trials as well. Okay, enough of MineSense specific. Let's look at how these systems work. So first for the shovel sense installs, same for the belt sense installs actually. We install a number of XRF sensors, and within each of these there is an X-ray emitter, X-ray detector, very much the same like a portable XRF analyzer. But then there is also a laser, and the laser is very important because the laser can see then when rocks roll into the bucket. That's when the X-ray emitter is started up. We start collecting an XRF signal. That XRF signal is transferred to the shovel, and there it's converted into a great prediction for that bucket. Distance is really critical here because that XRF signal is a function of distance, and so that needs to be corrected out. So we then have one great prediction per bucket. We integrate in real time with the fleet management system, so we know when the truck arrives and leaves. So we can then aggregate the buckets to that truck, and then we get our average truck rate, combine it with mine data to come up with the truck classification. If the truck classification is different from what the mine thought it was, then we generate the diversion message. And I think that whole integration is half of the picture. Like without the integration, the system wouldn't be used. There is no one in the mine who has time to look at this. It really needs to be automated to be useful. Each system is equipped with a positioning system as well. And so what you're looking at, each dot there is a bucket reading for copper content. You see the rams between the different benches. And what's in the background there, that is the blast hole copper grades. And so first thing why that 3D positioning is so important is just to validate. It's just to compare our shovel sense readings versus the blast hole readings to just validate that the predictions are accurate. Secondly is to pull in mine data. Like some mines, they decide what is ore and waste just on copper, but many use other variables like gold, recovery. And so to pull in those estimates which we don't measure from the local mine data to come up with the correct truck classification. So that's the second one. And then the third one is reconciliation and mine planning. So if you have your very high resolution data on one bench, for example, if you identify a dike, using then that information to inform where the dike on the next bench is. Or by extension, update your exploration model on the next few benches. So some examples. First, focusing on benefits from at-phase sensing. So what we're looking at here is a map view with all the triangles are blast holes colored against copper grade. The colored fields in the background is the mine geologist deciding what is ore and waste. All blue is waste, all orange here is ore. And then the dots on top are individual bucket readings by the sensor, colored also by copper grade. And the first thing you see is lots of waste that got blasted on top of the ore polygon, lots of ore on top of the waste polygon. All of this material, if you wouldn't measure it there, or if you wouldn't know that this blast movement happened, would have gone to the waste dump. So that's a lot of money right there lost. So I think that is a critical piece. And we see blast movement is often one of the biggest value drivers. Other value drivers are isolated ore. So some examples here of individual blast holes with plus 1% copper next to 0. And so being able to identify then those high-grade buckets and being able to pick them out drives a lot of value. Not shown here, but irregular contacts where it really switches from ore to waste, and there are a lot of diversions happening at those two. The fourth, which is one that surprised us, but which unfortunately happens, is that in the standard mining process with polygons, there is an individual coding that polygon. And if that individual makes a mistake, then hundreds of trucks go the wrong way. And we unfortunately see that happen sometimes too. And the last one is something you can't do much about. It's just operational requirements. If the crusher needs ore, the crusher needs ore, and then they will drop their cutoff. So, making mistakes, what is the negatives of those? Many. If you are dropping ore on your waste pile, you're going to make your acid mine drainage risk worse, and you're going to shorten your mine life. The other way around, if you drop waste into your crusher, you're using water, energy, production time for trucks which have no value. What does this sum up to? So this is results from last year across 9 mines. And this is the number of trucks that the mine accepted and actually diverted. So on average, over 9 mines, 5% of trucks that were destined for waste were actually recovered to stockpile or to crusher. 2% of all the trucks were removed from the crusher and sent to waste. These are significant numbers. This is 7% of trucks going the wrong destination. This is a large opportunity. This is at one mine, the best one. We had 5,000 tons of copper recovered. Now, the dilution piece is interesting because, okay, you're making room in your crusher for more ore, which will, if the ones you're replacing it with are high enough, you will increase your head grade, but you're also going to reduce the grade variability in the plant. And so the effect of that is shown here. So this is looking at plant data, showing on the x-axis the plant grade. So this is none of the ShovelSense grades. This is just what was measured in the plant versus recovery. And so you see a clear trend as the grade goes up, the recovery goes up. Very much expected, no surprises there. But then if we split the data between when less than 50% was covered with ShovelSense versus more, so this means that more than 50% of the trucks that were feeding the crusher had a ShovelSense reading, so had more dilution removed, is then the ID, that all of those show an increase in recovery. So I think that reduction in dilution has benefits beyond just not processing waste. It also actually improves the recovery at the plant. That was all the use cases of at-phase sensing. Going further down into the plant, use cases of how you would be able to use such sensors. Okay, I'll be rushing up. Okay, so quickly here, this is looking at copper grade through time. Each dot here is a truck rate. When the dot has a cross, it means that that truck was recovered from waste. And so there are a few here in the middle recovered from waste. Having a sensor in the plant, so this is a belt sense system, but it can be any system in the plant, actually nicely allows to confirm that those were indeed correct diversions. That was indeed ore that would have been thrown away. And on top of that, you can then connect to measurements from the processing plant itself, and you can validate that those are correct. Now, this is 2022, and at the time, these sensors had just come in, and there is a lot of variation at the mine phase. It gets blended out in the stockpile, but it's not all gone. There is still significant variation coming in. This mine subsequently implemented a dynamic crusher feed control, and the next slide tries to show that. So they installed one belt sense system after the first crusher, and they used that to measure the material coming in. And then they have been using that to then sequence these trucks so that the final grade going into the mill is almost perfect, zero variability going in. So I think it's the combination of these different systems that can drive a lot of improvements downstream. And then lastly, by having these data, then the metallurgist can use that information to better inform how to process. So this slide I'll talk very little about. This is just comparing, because the focus of MineSense has been mining and processing, but I think talking here, seeing everything everyone here works on, there is an opportunity in exploration too. So I'll just talk on these two. This is in the mine, ShovelSense data, looking at the response of copper versus the measured grade, and there are clearly two trends. This is a surface measurement. There is no pulverization or nothing happening. So when you would work through oxides, you'll measure a lot higher response. When you measure in sulfides, you're going to get a lower response. That's evident. And so we need to correct for that. At the moment, we do that with mine data. When you look back at the original exploration data that were collected, they also did surface XRF measurements. And they also see that same trend of surface oxides versus sulfides, how that surface to volume changes. So the opportunity here is, I think, can you use these observations to actually create a better informed plan of your mine that is then ready to get these new sensors to deliver the most optimal grade. And so conclusion slide. So in copper, there is a big challenge coming at us, is that we just need a lot more copper, and we don't really have the deposits to fill the gap. So I think what this audience a lot works on is finding new ones and then converting them into mines, but that comes with challenges. Finding them, getting them permitted, and getting then a license to operate and continuing to have that. So the call here is we should try to get more out of our existing operations too. I like the quote from Freeport. They talk about leach to the last drop. And so opportunities, we talked about reducing ore loss from waste, so be more selective at the mine phase, that's a 5% opportunity. Preventing waste from getting into the mill, that has benefits in terms of replacing that with ore and also optimizing flotation recipes. And then lastly, hasn't been explored too much, but how much can we learn in the mill with these continuous data streams and then actually improve the plan? I think that is actually a very significant opportunity still to be gotten. So understanding your mineral deposit, probably a two-way journey. Yeah. Thank you.
Great talk, Maarten.
Yeah.
As an XRF guy, I love this. I love this. Yep.
Maarten, thank you. Merlin Mar Johnson from Fitzroy Minerals. Is the cost of this system coming down quickly? Because I mean, you said they had an old system in 2022, and now they've got they've implemented. I mean, is the technology changing, and is the cost of installation falling? And how small does it have to be for an operation before it's kind of worthwhile putting this kind of thing in? I mean, would you put it in for a 10,000 ton per annum copper project, or is it only for the big boys?
We work with small and big mines. I mean, the smallest one we operate probably is a 30,000 ton a year mine. The biggest one is, yeah, they're very large. So the way pricing usually is not as a, you don't buy a system, you actually buy a service, and we sell as a monthly service. So the pricing would be adjusted depending on the value the system can generate. Yeah. Yeah. So absolutely worthwhile, I think. Yeah.
Well, thank you very much for the presentation. Very, very interesting. I think of a mining operation involves all kinds of technology, all kinds of materials. But if we just think of three, right? The human being, the truck, and the XRF. And you put a human being in a truck and you dump ore on it. The human being is going to be instantly killed because of the huge weight and the force and things like that. But XRF, my understanding of XRF technology is that it's even more sensitive than the human being. And I'd love to know a little bit more about how exactly this works, where you have something so incredibly sensitive, like an XRF analyzer,
Yep.
and a truck that is one of the most high endurance vehicles that has been constructed. How can one work with the other?
Good question, and probably our biggest challenge. So making these XRF sensors survive has been our biggest challenge. So we do install them near the top of the bucket. And then since between, I would say, 2016 and now, there have been massive improvements in shock protection, temperature protection of these sensors. So robustness has been our biggest challenge. I think we're at a stage where they survive between plant maintenance cycles, and then they are switched out. So I think, yes, robustness is a problem, but we see these systems as long as they survive between two plant maintenance cycles, we take them out and then we replace the bits that are broken. Yeah.
Okay, thank you very much.
One more comment? Yep.
That is a good question, though. I mean, the amount of shock, they had designed these sensors initially for military spec, but it's way beyond military spec, what you need for them to survive. It's, yeah.
Maarten's great presentation, really mind-blowing, actually. My question is, stockpiles. They are the repository of all sins, in my experience, and not just the copper grade. So what you end up with is historical stuff that doesn't have the data digitized, and You're left with a big pile, a rising copper price, management wants to reprocess historical stockpiles, go and sample them. Well, that's the first problem. Very difficult to drill. Anyway, if you can track the grades going onto your stockpile as you build the stockpiles, presumably you can put a 3D dumping position for every truck, along with a grade for every truck that goes to stockpile. Stockpiles aren't just made because of low grades, they're made because of problematic ores which have difficult chemistry. It can be zinc, arsenic, to begin to name them. So how many of those problematic deleterious elements can you also track with your current system?
Yeah, and good question. And that's where it's a combination. So some of them we can measure with these XRF systems. For example, arsenic is one of those we can measure. Lead, zinc in some copper mines is a problem too. But the idea is that the parameters that we can't measure, we actually have that positioning system. We have all the mine data preloaded on the shovel so that we then code the truck with all of the variables that matter to processing, and you track all of them to that stockpile. And then you create a stockpile model with everything you've got at that time. I'm sure in 10 years' time we need another set of variables, but what we have now. Yeah.
Brilliant, Maarten. Thank you so
Thank you.
much. Let's get you.